The next factor we need to discuss when we're talking about solutions and properties of solutions is a term known as solubility. So we're a little bit familiar with this, but not in a quantitative sense. Up to this point, we've just been saying, well, is something soluble in the sense that does it dissolve at all in water generally, or is it insoluble? Does it just not dissolve at all? We don't have a quantitative definition for solubility. And it turns out that the solubility of a solute in solvent is defined as the maximum amount of a particular solute that can dissolve in a given amount of solvent at a specified temperature. So temperature is important. We'll get to that in a little bit. And this is the maximum amount of a particular solute in that solvent at that temperature. Now, with this term solubility comes several other definitions that we should go through quickly and then maybe see an example of this. We'll also go through some of the various effects on solubility. So to start, we need these definitions. And the first is saturated. So if we talk about a saturated solution, what we mean is a solution that's in equilibrium with undissolved solute. Another way of saying this is a solution that contains the maximum amount of dissolved solute at that temperature. So if we take water and we dump copious amounts of table salt into it, eventually we'll get to the point where we can't dissolve any more table salt in it, and there will still probably be some solid table salt sitting at the bottom. That solution that's above that is termed saturated because we put as much into it as possible. And it just is now in equilibrium between the solution and the remaining solid material. We can't dissolve any more in. We can't get any additional amount into solution at that temperature. Now, with saturated, there's also another term that might seem a little bit confusing at first, and that is supersaturated. That's when a solution contains more dissolved solute than the amount that is normally achievable in the presence of excess solvent at that temperature. So supersaturated sounds like we've got more amount of solute dissolved than the saturated amount. And how could that possibly be? Well, it is possible, and that's where the definition comes in here. Then the amount that's normally achievable in the presence of excess solute at that temperature. The way that supersaturated solutions are formed is by heating the solution up. If you were to take that salt solution that you had, where you had some residual salt left over, and if you heated it up, you would be able to get more solute to go into solution. And we'll talk about the temperature effects later. But then if you cool it back down to the original temperature, if all of that solute stayed in solution, we would now have more solute in solution than we were able to get just by mixing at that normal temperature. And so we get a supersaturated solution. We'll see an example of this in a moment. Another definition, though, is crystallization. This is the process of solute exiting the solution to form an ordered crystalline solid, and I'll show an example of this in just a moment. Crystallization is when the solute is coming out of solution, but it has to come out of solution in an ordered fashion to leave an ordered regular solid. If the solute comes out of solution rapidly and doesn't form an ordered solid, but just forms a disordered random amorphous solid, that process is known as precipitation. That's more what we had encountered in chapter 4 when we were talking about precipitation reactions. In those cases, a reaction produces some insoluble material which just falls rapidly out of solution and doesn't form a nicely ordered solid. It just falls out as some powdery material. So here's an example then of supersaturated solutions and crystallization. So on the left, we have a solution where we've taken sodium acetate and dissolved it in water, but then heated the solution up and actually dissolved more sodium acetate than we were able to dissolve at room temperature. Then cooled it back down again, so we have a supersaturated solution. All of the sodium acetate is still in the solution, but there's more of it than we're normally able to achieve just by mixing at that temperature. Well, what happens here is that if you take a supersaturated solution and you provide it with some surface upon which to grow the solid. Solid normally needs some surface to begin to form an ordered structure, unless it's just precipitating out. But here, if we take a crystal of sodium acetate and drop it into the solution, that provides a solid surface upon which the material can grow. And so because there's more solute in solution than is normally achievable, that solute will start to crystallize out onto that crystal. And you see the very nice fine needles that are formed. We have a nice crystalline and ordered solid. And then eventually, all the excess solute that was in solution, more than the normal saturated amount, eventually all of that crystallizes out, and we're left with just a saturated solution, shown here, where we have now the full amount in solution that we're normally able to achieve, and we've got excess solute present, so those are in equilibrium. We have a saturated solution. So let's talk about some factors that affect solubility. There's a few different ones. First is the solute-solvent interactions. So how strongly interacting the liquid is, the medium, with the dissolved solid, or if it's a liquid. So there is a general rule here that substances that have similar intermolecular forces tend to be soluble in one another. And we talked about this back in chapter 11 when we were comparing hexane and water and carbon tetrachloride, and then also acetone and water, and saying some are soluble in each other, some are not, and it depends on the intermolecular forces that are present. And another way of expressing this is just by saying like dissolves like. Things with similar intermolecular forces dissolve in each other. Things with dissimilar intermolecular forces don't dissolve in each other. And we can illustrate this again with hexane and water. Water has dipole-dipole interactions and hydrogen bonding. Hexane has only dispersion forces. And so those two are not similar. They don't dissolve in each other. And again, we defined this in chapter 11, but we'll return to it briefly just to note that liquids that do mix well with each other are termed miscible, while those that do not are termed immiscible. So hexane and water are immiscible, whereas water and ethanol, for example, or water and acetone are miscible. Now, just a couple more examples here. If we look at cyclohexane, which has the same number of carbons as hexane, just they're in a ring now rather than all linear. Here we again note that it has no polar OH groups. It has only dispersion forces. And so cyclohexane is insoluble in water because of the differences in their intermolecular forces. But if you take a structure that's very similar to cyclohexane, this is a glucose, and you'll notice it now has many OH groups on it. It has a lot of hydrogen bonding capability. And so glucose is very soluble in water because of the hydrogen bonding that is present that's similar to water's intermolecular force. We can also compare this just by looking through a whole series of alcohols here that all we've done is increase the carbon chain, going from methanol down to hexanol. Methanol, we have a hydrogen bonding capability and only a small carbon-hydrogen region that's slightly non-polar, but then this is a polar molecule because of the net dipole with the oxygen and hydrogen here, and we've got hydrogen bonding. So this is completely soluble in water, infinitely soluble in water, but in hexanes, shown here, as a polar species with mostly hydrogen bonding, it's not terribly soluble, 0.12 moles per 100 grams of solvent here, so not terribly. As we extend the carbon chain, essentially what we're doing is we're just extending the non-polar region of the molecule. Carbon and hydrogen bonds are non-polar, so we're just basically, as we increase that chain length, we're just getting a longer and longer non-polar part of the molecule. And so as that increases, eventually we get to hexanol, which has a long non-polar region and only one region where hydrogen bonding is capable. And so the solubility in water decreases because we're going away from hydrogen bonding, now we're having more just dispersion forces from that nonpolar part. And so hexanol is much less soluble in water than methanol, whereas it becomes much more soluble in hexanes because of that nonpolar region, which is very similar to the nonpolar hexane. Another effect on dissolved materials is pressure effects. So this is really only a factor for gases. Pressure has very, very minimal effects for the solubility of solids or liquids in any solvent. But gases, the pressure has a significant effect on their solubility. So the solubility of a gas in any solvent is increased by increasing the pressure. We can do an example of this just by looking at dissolving CO2 in water. So any carbonated beverage has dissolved CO2 in water. And if you initially just take CO2 over water in some cylinder, then there will be a small fraction of the CO2 that will dissolve in water. But the normal solubility of CO2 at 1 atmosphere is relatively low in water. Again, I guess compared to perhaps dissolving ionic species or something along those lines. But if we take that cylinder and increase the pressure, that essentially just forces, essentially we've increased the partial pressure, and since that's in equilibrium with the solution, we're essentially just forcing more molecules to go into solution. So after equilibrium has been restored, we have more dissolved gas in the solvent. Now, this is actually the reason why if you take a carbonated beverage and you open it, why you hear that fizz and you see bubbles rising out of solution. The reason for that is because the carbonated beverage was pressurized, and then when you open the lid or pop the top, you've actually depressurized the system. You decrease the pressure. And so the opposite effect here is true. As you decrease the pressure, then the solubility of the gas decreases and more dissolved gas will escape from the solution. And thus, that's the bubbles that you see from a carbonated beverage. Now, there's actually a linear relationship between the solubility of a gas and its partial pressure. And remember, essentially, as we increase the pressure of the piston, we're essentially just increasing the partial pressure above the liquid. And there's a very nicely linear relationship between the solubility and the partial pressure, as kind of illustrated for these 4 gases here. And one thing that falls out of that linear relationship is something that's known as Henry's law. So Henry's law takes this linear relationship and actually equates and sets them into an equation. So we have here the solubility of the gas is equal to K times the partial pressure of the gas. So Sg is the solubility of the gas, Pg is the vapor pressure of the gas, and K is Henry's law constant, which depends on the gas identity. So O2, for example, will have a different Henry's law constant. This is essentially just the slope of this line. So O2 is going to have a larger Henry laws constant than helium, for example. So let's go through a quick example of how we would use Henry's law. So if we have the concentration of O2 in air-saturated water at sea level at 20 degrees Celsius is 2.9 times 10 to the minus 4th molar. So not terribly large. But if Henry's law constant for O2 is 1.38 times 10 to the minus 3 molar per atmosphere at 20 degrees Celsius, calculate the partial pressure of water, of the O2 that's above the water at this temperature. So we've been given the solubility, we've been given Henry's law constant. All we have to do is simply rearrange to solve for the partial pressure. That's just the solubility over Henry's law constant. Substitute those values in, and we would come out with a partial pressure above that water as 0.21 atmospheres. So that's how we would use Henry's law. There's certainly more complicated examples, but this is at least a brief introduction to the pressure effects for on solubility of gases.